What is up, multivariate gang? Today we are going to be talking about what is a vector. If you've been paying attention, you know I posted a video like this one a while ago, but it was too long and I did not go into enough detail about what a vector actually was because I was trying to make it not too long. So let's get into it. Alright, what is a vector? Alright, before we can talk about what a vector is, we first need to talk about what a scalar is. A scalar are the types of numbers that you guys have been working with so far. 3, 5, 7, negative 1063, and so forth. Just normal numbers. They are numbers, or let's call them quantities. They are quantities with a magnitude. And so there are lots of scalar quantities that you guys know. You know, you've got your mass, the distance between two objects, the speed at which you move, your net worth, stuff like that. All right. So several scalar quantities by their nature can only be positive. Mass can only be positive, distance can only be positive, speed can only be positive. Your net worth can be, but there are some that can be negative, like your net worth. You can, in fact, have a negative net worth. So if you have a scalar, actually we'll talk about the number line in a second. All right, first, got to talk about what a vector is. A vector is a quantity with a magnitude and a direction. Let's write that down. Vectors are quantities with a magnitude, if I could spell, and a direction. All right, do you guys remember Vector from the Despicable Me movie? That one super lame villain with the bowl cut who was like, I've got direction and a magnitude. His name was Vector. Yeah, that's what he was talking about. He's talking about this stuff. Now, vectors, you guys are going to know these quantities, and I'll go into more detail about these in a second. So you've got, easily the best way to describe vectors are in terms of movement. So there's your position. There's your displacement. There is your velocity. And there is your, well, there's acceleration, but let's go with force. You got forces. Okay. So you might be wondering, how are distance, position, displacement, how are those all different things? All right. So you got two people. They are 5 meters apart. That distance between them is a scalar quantity, 5 meters. Bam. But if these are the same person, if this person moved over here, that person had a displacement of 5 meters. But if all we knew is that person moved 5 meters, they could go this way, or 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 this way, so on and so forth. So to know where someone moved to, what their displacement was, we need to also know their direction. So in this case, they were displaced 5 meters in the positive x direction. Okay. Same thing with velocity and speed. You have a car. It's moving 60 meters per second. But if you just have a car that's moving 60 meters per second, you don't really know how it's moving 60 meters per second. You assume it's moving forward at 60 meters per second. But it could be moving backwards, 60 meters per second. It could be a flying car moving upwards, 60 meters per second. So how something is moving requires both how fast they're moving, which is their distance, but not their distance, their speed, but also requires the direction in which they are moving. And that is what separates velocity from speed. And forces. I think you guys will have all been in physics by the time you take this class. But you have a particle, you can push on it this direction, push on it this direction, push on it this direction, push on it this direction. Pushing on an object with a certain amount of force means nothing unless you know what direction that force was moved in. So there are two ways in two space. If we just have an XY plane, there are two conventions for describing a vector. Call that vector V. And that little fish hook right there, that's the way I will probably be denoting vectors. But another way that, especially with like electronic sources like your book will probably just have like a weirdly like emboldened letter to symbolize a vector. But I'm going to use these little fish hooks. So a vector can be described by its magnitude and its direction. It needs to be described by its magnitude and its direction. So there are two ways to describe a vector. You have either its x length and its y length. So x, y. And so if you know it's 3 long in the x direction, positive 4 long in the y direction, you can deduce its direction by like sine and cosine of all that. Sine theta equals 4 over 5, stuff like that. But if you know this angle and you know this magnitude and that 5, that's just Pythagorean theorem, what I just did. You can also say 5 units theta degrees. Really, you can just leave it like that, because when you talk about the angle that a vector is moved, the angle that a vector forms with the positive x-axis is usually its direction, the angle that it forms with the positive x-axis. But if you want, you could say theta degrees north of east, or if this was your theta, that would be theta degrees east of north. But this is the convention. Okay. I'm probably botching this, but this is just review for you guys anyway. Just getting some old wheels turning. That was -4. That would go this way. That was -3. It would go this way. Yeah. All right. So what if we have a vector whose point is not at the origin point? Okay, so let's talk about some terminology. This is a terminal point right here. Nope, that's not true. This is an initial point. The point where the vector begins. It's the terminal point. Or the point where the vector ends. So, and in this case, the initial point is at 3, 2, and the terminal point is at 6, 4. Nope, that's that's not true. 6, 6. Yeah. Okay. So let's say this was a displacement that somebody walked from the initial point to the terminal point, and also had a really long neck. How would you describe his displacement vector? I mean, you could find this length, and you could find this angle, and be like, blah blah blah. North of east or whatever. I can't spell. My bad, guys. But the most convenient way, by far, is to just have the x component of the vector and the y component of the vector. So how would we find the x component of the vector? Well, it would just be xt minus xi, yt minus yi. We just want to know the distance it went in the x direction and the distance that it went in the y direction. So we take the x component of the x of the terminal point, which is 6, subtract the x of the x of the initial point. Same thing for the y's. We get 3, 4. Easy peasy, no sweat. Okay, so that means that 3, 4 vector is the exact same as this other 3, 4 vector that we were talking about earlier. Like even though they start at different points, they have the same length and the same directions. So they are the same vector. Another way that you can describe a vector's components. So you can describe it as the change in x and the change in y, which is also the same as the x and y that vector would have if its initial point is at the origin point. And those mean the same thing. Those are just two different ways of thinking about it. I prefer the former way, just thinking about it delta x, delta y. Just makes more sense, I think. Okay, so during your other calculus classes, you guys have talked about at least these two things, displacement and velocity, or your position and velocity. You guys talked about those. It's like you had x equals 3t squared plus 7, which meant velocity equals just derivative with respect to time, 6t. And you guys probably don't remember having to ever find any angles or x components and y components or anything like that. And the reason you guys probably think of these as, you guys have been dealing with these as if they were scalar quantities. And the reason is a scalar quantity is a scalar quantity is effectively a vector quantity, but just along one axis instead of two like we have here. So you have your origin point, which is just 0. Then you have your points on the number line, 1, 2, 3, 4, 5. -1, -2, -3, -4, and all that. Whoops, what did I do? There we go. I have a point on the line. So the number 3 has a magnitude of 3 in the positive direction. And so if you have something its absolute value is 3, its magnitude is 3, it can be two places. It can either be here at positive 3 or it can be here at negative 3. So it has this magnitude and its sign describes its direction. And so whenever you would get a velocity that was positive, like if when t equals 1, velocity equals 6, that meant its velocity was of a magnitude of 6 in the positive x direction. And whenever it was negative, like when t equals -1, if you could go backwards in time, that would mean that velocity was 6, and it was your speed was 6, and you were going in the negative direction. Cool. Hope that was clear as mud. So those are vectors in 2 space, and we will probably talk about those as analogs, but the things you'll actually be doing the math with most of the time will be vectors in 3 space. And so a vector in 3 space, we have our delta y and delta x in 2 space, and we need a delta x, delta y, and also our delta z in 3 space. So let's pretend that this thing is not at the origin point. Just floating somewhere in 3 space. And we have our initial point, x initial, y initial, and z initial. We've got our terminal point, x terminal, y terminal, z terminal. And this vector can be described by xt minus xi, yt minus yi, zt minus zi. That's x component, y component, and z component. That's the most convenient way to describe it. Now, sometimes all you'll need to know about a vector is its length. And when that is the case, how do you find the length of this line? I'm sure you guys have guessed by now, or I might have alluded to it earlier. It's just the Pythagorean theorem. So if we call that delta x, delta y, and delta z, it is the magnitude of use these little double absolute value signs for the magnitude of a vector, equals square root delta x squared plus delta y squared plus delta z squared. And if you ever need to know like that angle or whatever, you guys just use sine, cosine, all that stuff like you normally would, and just treat all these as triangles. Cool. Hopefully that was simple. If it wasn't, you guys are smart. I'm sure you'll pick it up. We'll leave it there for now and pick up later with vector arithmetic.